Ever feel like you're just drowning in data, trying to find a clear signal in all that noise? Well, today we're handing you the toolkit. We're going to decode the language of psychological statistics and turn all that complex data into clear, understandable answers. So let's just dive right in. We ask ourselves these kinds of questions all the time. Does more screen time actually affect your sleep? Does a new teaching method really improve test scores? To answer any of this, we need a way to see if two things are genuinely connected or if it's all just a big coincidence. And that brings us to the first and maybe the most fundamental tool in our kit.
And that tool is correlation. At its very core, correlation is a statistical method that helps us understand the relationship between two variables. It's really all about seeing if they move together in some kind of predictable way.
And what you're seeing here gets to a really key point. Correlational research is non-experimental. What does that mean? It means we're not manipulating or changing anything. We're simply observing. We're looking at data just as it exists out in the world to see what kinds of patterns pop out. So, to make this whole pattern-finding thing precise, we boil the entire relationship down to just one single number. It's called the correlation coefficient. And this one little number is incredibly powerful. It tells us both the direction of the relationship and just how strong it is.
So, let's say we get a coefficient of +1. Well, we've basically hit the jackpot of positive correlations. This is a perfect relationship where both variables move in the exact same direction. As one goes up, the other goes up right along with it. A classic example is the more hours you study for a test, the higher your grade.
On the flip side, of course, we have -1. This represents a perfect negative, or you could say inverse, relationship. As one variable increases, the other systematically decreases. For instance, you might find that as the hours of TV watched per week go up, test scores tend to go down.
And what if the number is 0? Well, that's just as important. A correlation coefficient of 0 means there's no real relationship at all. The variables are completely independent of each other. The movement of one tells you absolutely nothing about what the other one is going to do. Okay, so we know we're looking for a number somewhere between -1 and +1. But how we calculate that number really depends on the kind of data we have. It's like having a toolkit, right? You need to pick the right tool for the job. Let's look at the two most common ones. Let's meet Pearson and Spearman, the two heavyweights of correlation. Think of the Pearson correlation like a super precise laser measure. It's perfect for continuous, numerical data, and it works best when the relationship forms a nice straight line. But it can get thrown off by extreme values or outliers. Spearman, on the other hand, is more like ranking the finishers in a race. It doesn't care about the exact times, just the order they finished in. This makes it fantastic for ranked data and way less sensitive to those pesky outliers. Now, don't worry, we are not going to get lost in the math here, but the whole goal of the Pearson formula, which we often just call R, is to figure out how well the data points fit onto a single straight line. That's why we call it a line of best fit. It's just measuring the strength of that linear relationship. Spearman's method is a bit different conceptually, as you can see here. Instead of using the raw numbers, the very first step is to convert all the data into ranks. So the smallest value gets rank 1, the next smallest gets rank 2, and you just keep going. Then you just look at the difference between the ranks for each pair and plug that into a formula. See? It's all about order, not the actual value. And this focus on ranks gives Spearman some really cool advantages. It's great for qualitative data, where you have an order, but maybe not a precise measurement. Think things like rankings or preferences. It's simpler to wrap your head around. And because one weirdly extreme value doesn't really change the order of the data, it's super resilient to outliers. Plus, it can spot what we call monotonic relationships, ones that are consistently going up or down, even if they aren't in a perfect straight line.
So, correlation is fantastic for telling us if and how strongly two things are related. But what if we want to take the next step? What if we want to actually make predictions? For that, we need another powerful tool in our kit: regression. Regression is what takes us from just describing something to actually predicting it. It answers the question, hey, if I know the value of X, can I make an educated guess about the value of Y? It helps us model that relationship so we can forecast outcomes. Now, regression comes in two main flavors. Simple regression is pretty straightforward. We use one variable to predict one outcome, like using how much you spend on ads to predict your sales. But life is rarely that simple, right? That's where multiple regression comes in.
It lets us use 2, 3, or even more variables to make a much more nuanced and accurate prediction. We're not just looking at ad spend anymore. Now we're also factoring in the season and what our competitors are up to. All right, let's level up. We've covered describing relationships and making predictions. Now let's get into the really advanced stuff. The power tools for when you've got these massive, messy data sets and you need to find the hidden patterns inside them. First up is factor analysis. Its main job, data simplification. A lot of data simplification. Imagine you have a survey with 50 questions about customer satisfaction. I mean, that's a lot to analyze. Factor analysis helps you boil those 50 variables down into just a few underlying concepts, or factors, like product quality, customer service, and price. Here's a really great way to think about it. If you have 50 different cake recipes, factor analysis is the technique that would look at all of them and identify the core ingredients that are common across most of them. You know, the flour, the sugar, the eggs. It finds the fundamental building blocks hidden deep inside your data. Okay, so our other power tool is discriminant analysis. Now this one isn't about simplifying data, it's about sorting it. Its main job is to take an observation and classify it into a group that we've already defined, all based on its characteristics. It helps you build a model that can accurately predict which category something belongs to.
And yeah, this slide just nails the analogy. You can literally think of discriminant analysis as a sorting hat for your data. You feed it information about a new customer or a new patient, and it uses everything it's learned from past data to place that new observation into the group where it most likely belongs.
Phew! Okay, we've covered a ton of ground, from simple observation all the way to complex classification. So let's wrap this up with a quick recap, putting every tool back in its place so you know exactly which one to grab for any given task. Think of this as your statistical cheat sheet. If you just want to know if two things are related, you use correlation. If you want to predict an outcome, you use regression. If you need to simplify a ton of variables down into core themes, you're going to grab factor analysis. And if your goal is to sort and classify data into groups, well, discriminant analysis is your tool. Each one answers a very specific, very powerful question. And that's really the big takeaway here. These aren't just abstract statistical methods. They're lenses for seeing the world more clearly. They are tools for uncovering hidden relationships and making sense of all the complexity out there. So the final question is, now that you have the toolkit, what hidden patterns are just waiting for you to discover?